Okay, this is electronic devices 18 EC 33 module 0 lecture 1. Module 0 I have put only to refer to what is necessary to study this, right? What is necessary to study this, or rather review, or sometimes we call it as prerequisite. So might be 1 or 2 lectures we need to go for through the so to say review classes only about what is needed for the syllabus. Exact syllabus where it starts, I'll tell you at that point. Okay. So this is the detail about the semiconductor industry. The semiconductor in devices such as diodes, transistors, integrated circuits can be found everywhere in our daily lives. In Walkmans, televisions, automobiles, washing machines, and computers, some of the uh, places where the semiconductor devices are used are being mentioned over here. And then equally well, because of the semiconductor industry, we have the personal computers being developed, and the present day computers are very fast compared to the olden day computers, and the cost of the computer also is very low compared to the earlier computers. So as time passes, we see that we are getting more and more powerful computers for lesser and lesser rate, cheaper and cheaper. Okay, price is reducing, but the power of the computer is increasing. That's what we see if we see the different generations of computers which are happening, right? So because of this, the basic reason why this is happening is because the semiconductor devices such as transistors, diodes, and all that are becoming smaller and smaller. That's why you see that we are having lesser and lesser micron transistor. We generally call it as 50 micron, 20 micron, 10 micron, 5 micron technology. So micron just means it is so small, 10 to the power of -6. So definitely 5 micron is much smaller than 20 micron. And as time passes, the number of transistors which you can put in a single chip is going on increasing. And because of that, you have, less power consumption, more and more performance and speed, and also lesser and less cost. Size also is reducing. All that is being mentioned over here, right? So here we will be trying to see some of the definition of semiconductor, number of electrons in the outer shell, location in the periodic table, then crystalline structure of the silicon. Then this is might be our proper syllabus: intrinsic, extrinsic semiconductor behavior, know how to affect the behavior through doping, explain in detail what depletion layer and how they are formed, and then the PN junction. So this slide set gives us all that, but we might not be bothered about all that. In the review, we might be considering only the first two. Really speaking, our syllabus starts in the 3, 4, and 5, which corresponds to the module 1 and then module 2. So semiconductors, they are there, here, everywhere, right? In computers, Palm Pilots, you have silicon, MOSFETs, ICs, CMOS, and all that. Then cell phones, you have silicon ICs, gallium arsenide, FETs, BJTs, CD players, you have ALGA, AS type of, so to say, laser diode, INGAP, laser diode, silicon photodiodes, TV, remote, and mobile terminals. We have the light emitting diodes. Then satellite dishes, we have the indium gallium arsenide. So like that, fiber networks are use the INGA ASP. You can see that 4 different materials are being used over here. Here 3 different materials. Here 2 different material. Here you have a single material, silicon. This is 2 different materials joined together. This is 3 different material joined together, and this is a 4 different material: indium, gallium, arsenic, and phosphorus. Laser diodes are pin photodiodes. Then traffic lights, you have the gallium nitride LEDs, which might be green or blue. Then even car tail lights, which use indium gallium arsenide phosphate. LEDs, red and amber. Airbags, which are used in the vehicles, they use silicon MEMS and silicon ICs, and these are, this semiconductor is rather very much important in the electrical engineering and the computer sciences. So semiconductors are materials we know whose electrical properties lie between conductor and insulator. A conductor conducts very heavily, a insulator does not conduct at all, whereas semiconductor electrical properties lies somewhere in between. So the semiconductor acts as a insulator under normal conditions, whereas when it's properly doped or when we give heat to it, then thermally generated electrons are there. They'll cross what is known as the band gap and hence become the conductor. So when you provide some sort of doping and voltage, a semiconductor gets converted into a conductor. Till then it will remain a insulator. So examples of the semiconductor are silicon and germanium. Initially germanium was used quite a lot. Later we see that silicon has picked up quite too much. So examples of the conductors and insulators, there are quite a good number of conductors we know very well, aluminum, gold, silver, for that matter, any metal is a conductor. An insulator might be wood, glass, or such different things, will correspond to a insulator where there is no conduction of electricity. So it's basically the difference in conductivity which decides what a conductor is, what an insulator is, and what a semiconductor is. So for insulators, the conductivity is 10 to the power of minus 18, mho inverse, meter inverse. Okay, this is conductivity, and in the semiconductor, it is somewhere between 10 to the power of minus 8 to 10 to the power of minus 3. Mho inverse, meters inverse. For conductors, it is 10 to the power of 18, mho inverse, meter inverse. So 10 to the power of 18 here, 10 to the power of minus 18 here. It's somewhere between 10 to the power of minus 8 to 10 to the power of minus 3, mho inverse, meter inverse. So semiconductor materials, when we talk about elemental semiconductor, it is silicon and germanium. Column 4 of the periodic table composed of the single species of atoms. Okay, single species of atoms, silicon and germanium. Compound semiconductors, combination of atoms of the column 3 and 5. So here, when we talk about elemental, it is the column 4, whereas the compound semiconductors combination of the column 3 and column 5, and some atoms from column 2 and column 6 joined together. So combination of two atoms results in binary compounds. We call this as binary compounds. So binary compounds, here you have elemental, you have, so to say, column 4 compounds, which are silicon carbide, silicon germanium combination, whereas binary 3-5, that is column 3 and column 5 compounds, which are basically binary compounds, are aluminum phosphate, aluminum arsenic, aluminum tin, gallium phosphate, gallium arsenic, gallium tin, indium phosphate, indium arsenic, and so on. Then binary 2 and 4 compounds. So this is binary 2 and 4 compound, that is the column 2 and column 6 compounds together. The two columns, column 2 and column 6 joined together might give zinc sulfide, zinc selenium, zinc terinium, cadmium sulfide, cadmium selenium, and so on. So these are binary. Similarly, you can have the ternary compounds such as, 3 element, that is ternary compounds such as gallium arsenic phosphate, or 4 elements which are known as quaternary, which are indium gallium arsenic phosphate. So these are also there in the for new what you call devices, but might be quite rare. So this is how the periodic table looks like. This is the column 4, where you have carbon, silicon, germanium, so to say, tin what is SN? SN might be, just check it up. And PB, it is lead, right? All these are the, so to say, uh, semiconductor materials. Elemental, elemental semiconductor materials correspond to the 4A, right? So the wide variety of electronic and optical properties of these semiconductors provide the device engineer with great flexibility in the design of electronic and optoelectronic functions. So initially, gallium was widely used in the early days uh, uh, for development of transistors and diodes. Then later, silicon is presently used in majority of rectifiers, transistors, integrated circuits, and so on. Then compounds are widely used in high-speed devices, particularly gallium arsenide and all that, and devices requiring emission or absorption of light. Electronic and optical properties of semiconductors are strongly affected by impurities which are added to the what you call pure silicon, pure semiconductor, and these impurities are added in a precisely controlled amount. That is, an impurity concentration of 1 part per million can change a sample of silicon from a poor conductor to a good conductor of electric current, but only when you give some voltage to it. So this process is called doping. So adding the impurity to a pure semiconductor is known as doping. Adding a what you call impurity, generally we call it as trivalent or pentavalent impurity to the so to say semiconductors such as silicon, germanium will is known as doping. So if you give the pentavalent impurity, then you will get the N type. If you add the trivalent impurity, you will get the P type uh, material, P type semiconductor device. Okay, P type and N type. P type just means one shot of electron that will correspond to trivalent. Uh, N type just means one more electron that corresponds to pentavalent. Okay, then the silicon and germanium. Silicon and germanium themselves have 4 electrons in the outermost orbit. So let us see the solid state structure. A crystalline solid is distinguished by the fact that atoms making the crystal are arranged in periodic fashion. That is, there is some basic arrangement of atoms that is repeated throughout the entire solid. So some basic arrangement of atoms, which we generally call it as, might be uh, polycrystalline solid. Either you can have polycrystalline or even for that matter amorphous solid. That is, there is some basic arrangement of atoms that is repeated throughout the entire solid. Thus, crystals appear exactly the same at one point as it does at the series of other equivalent points once the basic property is discovered. However, not all solids are crystals. Some have no periodic structure, such as amorphous solids, and others are composed of many degrees of small single crystal material, such as polycrystalline solids. So we have 3 different things over here: crystalline, amorphous, and polycrystalline being mentioned. So they have a particular, structure, whereas these are random. So therefore, these are amorphous, and this is crystalline, and this is polycrystalline. So that is partly amorphous and partly, crystalline. So the periodic arrangement of atoms in crystal is called a lattice. Whatever way the atoms are arranged in a crystal is generally called the lattice. The lattice contains a volume called a unit cell, which is representative of the entire lattice. So might be one unit cell will keep on repeating throughout, and hence become the total, material, solid crystal material. And this unit cell is repeated regularly throughout the crystal. So you have a cubic lattice like this, then cubic lattice is shown here, simple cubic is here, body centric cubic is here, and face centric cubic is here. So diamond lattice unit cell. This is a diamond lattice unit cell showing the four nearest neighbor structures. Four nearest neighbor structures. The basic lattice, this you can see that this is the diamond lattice, and to this you have four neighbors, right? So basic lattice structure for many important semiconductors, the diamond lattice, which is the characteristic of silicon and germanium. And in many compounds, uh, compound semiconductors, atoms are arranged in the basic uh, in many compound semiconductor atoms arranged in a basic diamond structure but are different in on alternating site, and this is called a zinc blend lattice, and this is typical of the 3,5 compounds. The diamond lattice can be thought of as an FCC structure. Okay, we generally call it as an FCC structure with an extra atom placed at A by 4, B by 4, and C by 4. Okay, A by 4, B by 4, and C by 4. This is the position might be, which is A by 4, B by 4, C by 4 for each of the FCC atom. So other type of solid state structures such as the diamond lattice of silicon and germanium, and then the zinc blend crystal architect structure of the gallium arsenide and indium phosphate is being shown over here. So this is a single type of atom here. Two different types of atoms. Some of them gallium and some of them arsenic, or some of them indium and some of them phosphate. Okay, each atom in the diamond lattice has a covalent bond with four adjacent atoms, which together form a tetrahedron. This lattice can also be formed from two FCC cubic lattice along the body diagonal of the larger cube in the figure by 1/4 of that body diagonal. The diamond lattice, therefore, is a FCC cubic lattice with a basis containing two identical atoms. So diamond lattice is a FCC cubic lattice with a basis containing two identical atoms. Okay, so how does the atoms and electron looks like? You have the core here, and then you have the what you call so to say bands. You have the shells or bands. Sometimes we call them as shells, and sometimes we call them as bands. So we shall investigate some of the important properties of electrons with special emphasis on 2 points, that is electronic structure of atoms and interaction of atoms and electrons with excitation, such as absorption and emitting of light. So this will be the case in case of the photodiode. By studying electron energies in an atom, we lay the foundation for understanding the influence of the lattice on electrons participating in the current flow through a solid. One of the most valuable experiments of modern physics is the analysis of absorption and emission of light by atoms, which is generally, used in case of, photo diodes and such things. So, for example, electrical discharge can be created in a gas so that atoms begin to emit light with wavelength characteristics of the gas. The result of emission spectra experiments led Niels Bohr to conduct a model for the hydrogen atom based on the mathematics of planetary systems. If an electron in the hydrogen atom has a series of planetary type orbits available to it, it can be excited to an outer orbit and then can fall to any one of the inner orbits, giving off energy corresponding to one of the lines seen in the spectrum. So this might be inside you have the core, then you have the different orbits. From a lower orbit one, it can go to a higher orbit. Electron can go to a higher orbit by properly, exciting the what you call the electron. Okay, by giving energy to it. If you withdraw the energy, it might come back to the what you call inner orbit. That means by emitting the energy, it will just come back. So it takes energy, and an electron takes energy and goes to the higher shell. It emits energy and comes back to the lower shell. or lower band, as it is sometimes known as. So Bohr developed the model which is generally specified with these two properties. Electrons exist in certain stable circular orbits about the nucleus. Stable, certain, it is very important to check this, certain stable circular orbits about the nucleus. So you have the nucleus here and you have the orbit, and electrons exist in the certain stable circular orbits. The electrons may shift to an orbit of higher or lower energy, thereby gaining or losing energy equal to the difference in the energy level. So between two shells, you might have two levels, you might have a different, you will have a difference in energy level. So by giving energy, the electron moves from a lower orbit to a higher orbit, from a lower band to a higher band, or lower shell to a higher shell, right? It will be able to go. And similarly, when it emits the energy, then it can come back from a higher level to a lower level. So thereby gaining or losing energy equal to the difference in the energy levels by absorption or emission of photons of energy which are there in it. However, the simple Bohr model, which accurately describes the gross features of hydrogen spectrum, did not include many fine features. Bohr did not give more fine features. These features are described later by principles of quantum mechanics. So finally, the work of Bohr, Boltzmann, Planck, Einstein, and others has developed an understanding of the atomic structure, which shows that electrons circle the nucleus in orbit, having different associated energies. So you have the nucleus here, and electrons, what you call go round and round. That means they will, what you call, so to say, revolve around the nucleus, right, in different orbits. So developed an understanding of atomic structure which shows that electrons circle the nucleus in orbits having different associated energies. Circle just means they'll go round and round. The electrons also spin on their own axis. These electrons also spin on their own axis. The energy of the electron is quantized in that only certain discrete levels of energy can be possessed by electron. So we see that not all energy levels the electron can take, but only certain energy levels electron can take as it shifts from one orbit to the other orbit, or one level to the other level, or one shell to the other shell. So the energy of electron is quantized in that only certain discrete levels of energy can be possessed by the electron, and no values in between these discrete levels are allowed. The levels exist in groups which are referred to as shells, and there are subshells within the main shell. So this might be a shell with, it might have a subshells here, 4 of them. Similarly, this might be a shell, and you have here the shell structure where there might be 8 so to say sub shells over here. So silicon Si is the group 4 material, we know all that, which is having the atomic number 14. Consequently, it has 14 positively charged protons and 14 neutrons, and it has 14 orbiting negatively charged electrons, 2 in the full K shell. So there are only 2, this is K shell, and 8 in the full L shell, and that is, this is L shell, and 4 in the half full F shell. This is M shell. This is the inside one is K, L, M. Okay. Within a full half full outer subshell, the atoms have an affinity for 4 additional electrons to try to complete the outer subshell. So if there are 8 together, then we say that they are full. But the 4 plus you have 4 over here, so still a vacancy of 4 is present. So you have a Pauli's exclusion principle states that no 2 electrons in an atom molecule can share the same exact quantum specification. In practice, this means that no more than 2 electrons can share precisely the same orbit or energy level. and the two must have opposite spins. Okay, so silicon atom looks something like this. With the covalent bond, you have the silicon atom with the covalent bonding between them. Two atoms might be joined like this by means of the covalent band. That is, they share this will share four of its electrons with this, or might be on this side it shares two electrons, on this side it shares two, or rather this shares, two electrons with this, two electrons with this, two electrons with this, and two electrons with this. So totally it will become 8, and those